Oh, yeah. People I don't see. Do not see Daisy or Andrew. All right, the Doppler effect. Just 2 slides on sound remaining. The first one is the Doppler effect. Who knows what the Doppler effect is?
It's when something's far away, you vaguely hear noise, and then when it gets closer, it becomes louder. Is that right?
It's right, except for one thing. It's not that it gets louder. It's a different thing. The pitch. When something's coming towards you, the pitch is a higher frequency. When it's going away from you, it's a lower frequency. I still remember when I came to America, one thing, parents, this kid's lived in Africa for 5 years, he's got to see what America's about. So they take us to Disneyland. And as like a 5 or 6 year old, it probably was when I was 6, because you have to wait till dad gets a job before you can afford to go to Disneyland. We go on this thing that's called the People Mover. And the People Mover, of course, to any adult is really boring. But it's just a slow little trip around the park where you see all the different things they have going on. And in one part where you're just going through this little enclosed area, they called it the super speed tunnel. And they used projectors to project on the walls things like motorcycles racing past you, and then cars racing past you, and it merges from one to the next. And along with that, they have sound effects, and they blow air in your face. And as a little 5 or 6 year old, that was enough to convince me that there really were motorcycles and cars racing by me. Okay, so I wasn't super logical. But of the thing that convinced me the most, it was the sound. Because seeing the motorcycles come at me was one thing, but having the sound effect, which goes meow as they pass, I was like, oh, that's exactly what happens, when you pass them on the highway. It's got to be real. That effect, the sound effect, is the Doppler effect. And the Doppler effect is actually caused by a very simple situation. So here's a picture to illustrate the Doppler effect. We have the observer, who in this picture is standing stationary, and a car is driving toward him. And the car, its motor is making sound. And so its motor might be making sound with the, let's say, frequency is 100 hertz. If the frequency is 100 hertz, then what's the period? Okay, the period's going to be 1 over the frequency. So 1 divided by 100 hertz. What does the abbreviation hertz actually mean? 1 per second. So if I'm dividing by 1 per second, invert and multiply, it's going to have seconds on top. This is going to be equal to 0.01 seconds. So that means every 0.01 seconds, the sound is reaching its high point, right? You have a sound wave that's going like this. The period is the time for it to repeat. So every 0.01, it hits that high point. So if the car was stationary, it would have sound waves coming out with the separation between them. What do we call the separation between the sound waves? The wavelength. And that wavelength is equal to the distance that the sound wave travels in one period. So that'd be the speed of sound multiplied by the period. Does that make sense? If the car was stationary, that's what would happen. Setting sound out, the sound is traveling at V sound, and a time of the period is the time between when each peak leaves. So the distance between them is going to be the speed at which it's traveling multiplied by the time between them. So that's if the car is stationary. But what if the car is moving? If the car is moving, then in the time t, 1 period, so I'm going to not redraw my picture, just change colors for moving. in the time of one period, the sound wave moved forward that same distance, but the car also moved. How much does the car move if the car is moving at V source? How far is it going to move in the time between when it emits sound waves? If I'm driving the car at 30 meters per second, how far is it going to travel in 0.01 seconds? Okay, how did you get that, Tyler? It's going to be the speed, not sound now, it's the source, multiplied by the period. So the wavelength is going to be shortened by that amount because the car was chasing after the wave. So the wave didn't get as far away from the car in one period because the car was chasing it. So I have a shortened wavelength. Now if we convert these to frequency, frequency is equal to the speed of sound, SND is what I use for sound, divided by the wavelength. Then I can relate the frequency with the car moving to the frequency with it stationary. Note if the wavelength is shorter, what's that going to do to the frequency? It's going to make it go up. So what I'm going to do with my work here is I'm going to take the top equation and solve it for V. Well, let's see, what's the best? Trying to remember what the best way is to go from here. Of course, that's frequency is 1 over period. And if I take the lower one, I have frequency prime is equal to V sound over, and I can factor out the T. So I'm going to replace the 1 over period with frequency that it would have if it was stationary. And so that's our equation for the Doppler shift. The frequency that you actually hear if the car is driving toward you is equal to the frequency the car is emitting times this ratio of the speed of sound divided by the speed of sound minus the speed of the source. This sign is for the car coming toward you at speed V source. What if we went on the other side? What if the car was moving away from us? So it's going in the opposite direction as the sound wave. What would that do to the wavelength? It would make it have a longer wavelength and thus a lower frequency. And so this equation works in both cases. Just use a negative speed for the source if it's moving away and a positive speed of the source if it's moving toward you. So that's our equation for the Doppler shift. It's really pretty simple. And so as the object is coming toward you, you hear a higher pitch. So I'm going to draw a line on here for there's the actual frequency the car is emitting. As it comes toward you, you hear a higher pitch. When it passes, it shifts to a lower pitch, and then you hear the lower pitch as it's moving away. What would happen if the car was doing a circle around you? The same. Why?
Because it's not getting any farther.
Right. It's not getting any farther or closer. It's not chasing the wave. It's just going around a circle. So this only has to do with what we call radial velocity, the velocity going straight toward or away from you. From the Doppler shift, the non-relativistic Doppler shift, you can't tell anything about the transverse velocity, how quickly it's going in a direction perpendicular to the line connecting you. Now, I've only done half of the Doppler shift here. What's the other half? The other half. You could have the observer moving. If the observer is moving toward the source, that's again going to shorten the wavelength and thus raise the frequency. If the observer is moving away, it's going to lower the frequency. The work for that is analogous to what I did, but you don't get the same equation. And so it turns out that if you include both a moving source and a moving observer, V sound V sound plus V observer over V sound minus V source, where both the velocity of the observer and the velocity of source are going to be positive numbers if they're moving toward each other. So the sign convention is V obs is positive if observer approaching source. V source is positive if source approaching observer. So that's our full Doppler effect. And it's a cool effect that you hear all the time. You're out there on the street, you hear cars coming toward you, passing you, you hear the Doppler effect. Don't have to have high speeds for it to be observable. Something I don't have any slides for. I'm going to make a blank slide just for this. What would happen if something was coming toward you and it was going faster than the speed of sound?
You would hear it telepathically.
Okay? I'm going to draw a picture here. So I'm going to have something is here, one period later it's here, one period later it's here, one period later it's here. And let's say it's going faster than the speed of sound. So the sound it makes at the first point, at the time it's at the second point, that sound wave has only gone out this far. In that case, it's exactly what Andrew said. That sound doesn't get to you until after the aircraft does. Of course, it's an aircraft, right? If it's on land, you're really in trouble. What actually happens is you form a cone of sound. And on these lines that I drew, those lines we call shock waves. And what happens on those shock waves is you have sound from multiple times all merging together so you hear it at one time, right? Sound that was produced over a course of maybe 3 seconds, you hear in 1/100th of a second. Well, if you have the energy that was produced in 3 seconds and you hear it over the course of 1/100th of a second, what is that going to do to the sound? Let's try this a different way. We can put it into mechanical terms. You might have answered right. I didn't hear you, Denford. Let's say that it took you 3 seconds to pull this weight tied to a rope up 6 feet. And then you let go and it hits your toe all at 1 second. Right? The energy you put in 3 seconds is returned to your toe in 1/100th of a second. What's the effect? It's really intensified because you took all that energy and put it on a short time. So the power goes way up. So in this case, when you have that shock wave, the sound waves are all adding up and it's much louder. And of course, what do you tend to call that sound wave? Okay, the aircraft is going supersonic and it creates a sonic boom. So that shock wave is a sonic boom. You used to hear them more than you do these days. Like when I was in graduate school, they used to have aircraft from the nearby Air Force Base, well, nearby, 60 miles away. They would, 3 or 4 times a year be close enough to us when they were above the speed of sound that you would hear the shock waves. But then they started saying, okay, we're going to do this out in more remote areas. Granted, Washington State University is pretty remote for those paying attention. But I haven't heard a shock wave in a long time, a sonic boom in a long time, whereas you used to hear them reasonably regularly. So that's what makes a sonic boom, something going faster than the speed of sound. If you look at our equation here, if the speed of the source is equal to the speed of the sound, what are you dividing by? You're dividing by 0, which means your frequency would have to be infinite. Right? That's where that equation breaks down. So that equation is only good up to the point where it's traveling the speed of sound. If it's going faster than the speed of sound, it starts giving you negative frequencies. Well, negative frequency actually isn't a problem. It's still going to be a positive frequency. It's just telling you you're hearing the sound backward. So if somebody in there was saying, help, you would hear, or whatever. Which is kind of cool, huh? I think it is. I mean, you guys are no fun. Okay, so we got the sonic boom covered. It's kind of cool. You can actually experience a shock wave much more easily. Because if you're in a boat, you have water waves, right? Speed for water waves is pretty slow. And with the boat, when the boat exceeds the speed of a water wave, what happens? It creates a V-shaped wake. That wake is also a shock wave. So the sonic boom is a sound wave where you had something traveling faster than the speed of sound. A wake is a water wave where you have something traveling faster than the speed of a wave in water. And in both cases, you can actually, if you measure this angle right here, that side there is going to be speed of sound multiplied by time. This side here is the speed of the object multiplied by time. And so this angle, I'm rewriting the angle so you can see it more clearly since I put it way out there. That angle, if you relate those two sides, opposite side over hypotenuse is sine. Well, object, it's the source. Cancel out the times, and you can measure the angle and determine the speed of the object compared to the speed of sound. Or likewise, for a boat, if you measure the angle of the wake and how fast the boat is traveling, you could then determine what the speed of a wave is in the water. Okay, that was one of 2 slides, 20 minutes. 2 of 2 slides. Well, this is just on the Doppler effect again. And so I think I've covered it enough. I'm not going to spend time on it. And move to new topic. What causes color? What causes reflection? Pretty picture here of the light, different colors in a soap bubble. And so that's what we're going to explore in now chapter 16. So start with a clicker question. This is asking about your pre-knowledge. I'm going to ask the question again after I lecture on it, but right now just what you think about what do light, radio waves, microwaves, and X-rays have in common. Okay, we had 3, 0, 0, 3, 1. Is that legible color? Yeah, it kind of works. Change to my white pen. Okay, these waves, first of all, the key for these waves is these are all forms of electromagnetic waves. Which means they all have the same properties. So it's going to be anything that's true for one is true for all. First thing I'm going to talk about here is medium. A sound wave, we talked about sound waves as being basically chain reactions. Molecules come out of my mouth, they hit other molecules, and the chain reaction brings the sound wave to you. What kind of wave is a sound wave in terms of transverse and longitudinal? It's a longitudinal wave. Okay, a longitudinal wave like a sound wave absolutely requires a medium. That is, it has to have something it's going through. You can't just have it go through a vacuum. If you watch movies like Star Wars and you have your physics brain going, you say, that's so ridiculous. You have things like somebody blows up a ship and the guy in the other ship hears it blow up. No, they're supposed to be fighting out there in the vacuum of space. There's nothing to carry the sound wave. You don't hear it, it just goes, right? There's no sound effect. But because we know that on Earth, if we had an explosion nearby, we'd hear it, to make theater goers feel the excitement and relate to it, they play sounds. I mean, surely by now the movie makers know, yeah, that's unrealistic, but we're going to do it. You know, you fire your photon torpedoes and, pew, 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 as they come flying by you, you would hear something inside your ship that's generated in your ship, but once it leaves your ship, you wouldn't hear it. If it's generated from another ship, you're not going to hear it unless it hits you. Right? Near miss is just... So there's no sound in the vacuum of space because there's no medium, and you have to have a medium for a sound wave. But electromagnetic waves, it turns out, don't require a medium. So they can travel through empty space. Initially, when scientists were studying electromagnetic waves, they didn't think that was possible. They said there has to be a medium. There's a medium for all the other waves. And so they called the medium ether, some ethereal substance. And they did a lot of studies to try to identify the properties of this ether. And all of their studies came up with null results. That is, we got nothing. We can't see any differences. They did things like, well, if you are with the Doppler effect, you're traveling this direction, you got one response, this direction, another. Try doing things like having two receivers set up and travel this direction, measure the speed of light, then rotate and travel this direction, measure the speed of light. If you did that with sound waves, you get different results because of the speed of the air. But with electromagnetic waves, they found no difference. So that's how they came up with, we were wrong, there is no medium for electromagnetic waves, they just travel through vacuum. And in fact, they travel the fastest in vacuum. You put something in their way, even air, that slows them down. Not very much. Put glass, that slows them down a lot more. Put diamond, that slows them down a lot. Okay, they all travel at the same speed. Now this one here is kind of tricky. I should have said in the same medium. Electromagnetic waves don't need a medium, but if they have a medium, then that's going to affect the speed. And even in that case, the same medium is not perfect. I really, now that I think about it, it needs to be in vacuum. One C or two in vacuum? One? Okay, so they all travel the same speed in vacuum. That's true. We call that speed the speed of light. in vacuum. So we have a special symbol, the letter C, to represent the speed of an electromagnetic wave in vacuum. And whether it's an X-ray, a light wave, a radio wave, or a microwave, they all travel at the same speed in vacuum. Finally, they all have no mass. Yes, indeed. Waves don't have mass. So all of those were true. Hence, D was the correct answer. Now, any questions about these answers? Like I said, we're going to have this question come up again.
Well, yeah, are we supposed to always assume that when you're asking they don't have the same speed, should we just assume that you mean in vacuum?
Assume I mean in vacuum unless it says otherwise. Because, yeah, it changes the answer if it's otherwise. Hence the reason prisms work. So here's what an electromagnetic wave looks like. Of course, I could be all stupid on you and say, look at me. That's what an electromagnetic wave looks like because your eyes are detecting electromagnetic waves. But that really wouldn't be useful. So electromagnetic waves are oscillations of white on white. It's the best viewing ever. Electric field. Actually, I should have used green. And magnetic field. Now, there's some cool things to note here. It turns out James Clerk Maxwell is the one who put the math equations together that predicted that you could support electromagnetic waves. Waves of electric and magnetic fields that are oscillating. But things that are really cool here are the electric field is always perpendicular to the magnetic field. And notice they're perfectly in phase. At the time when the electric field is the strongest, the magnetic field is also the strongest. When the electric field is 0, the magnetic field is 0. And in fact, the electric field and magnetic field are always perpendicular, and both of those are always perpendicular to the velocity of the wave. So if a wave is going from me to Zach, I can tell you that the electric field has 0 in this direction. Right? The electric field has to be in a direction like this. Likewise, the magnetic field has 0 in this direction. It has to be perpendicular to the velocity. So electromagnetic waves are oscillating electric and magnetic fields. The two oscillate together, and in fact, the magnitude of the electric field is just proportional to the magnitude of the magnetic field. So when we talk about electromagnetic waves, we usually simply say, okay, I'm going to talk about just the electric field. Because if I know the electric field, I automatically know the magnetic field. I know its strength. I know everything about it if I know the electric field. So we just, by random decision, talk about the electric fields when we have an electromagnetic wave. But you have both the electric field and the magnetic field oscillating. And so here's how you make a radio antenna. Very simple. You have a sine wave oscillator, and so that's going to make current, let's say current goes like this. So if current's going like that, you use your right hand rule, point your thumb in the direction of the current, and your fingers wrap around the direction of the magnetic field it creates. And so it's going to create a magnetic field that's doing circles. And you have an oscillator so that current direction is shifting. So I drew it first going up, but then a little bit later, the current is going like that, and it reverses the direction of the magnetic field. So if you look here, you see the arrows are shifting directions. Here the two arrows are going around it one direction. Here they're going the opposite direction. The magnetic fields are shifting back and forth as the current shifts back and forth. So this creates oscillating magnetic fields. And the oscillating magnetic fields will then create oscillating electric fields, and the two work together to make an electromagnetic wave. What did I say about the direction of the velocity compared to the direction of the magnetic field? Denver? Perpendicular. So if the magnetic field is doing these circles, then the velocity has to be perpendicular to that. it also has to be perpendicular to the electric field. If the current is going up and down, you're going to have, you're going to have things like positive charge on top and negative charge on bottom and then flipping back and forth. And so the electric fields are going to point up and down like this. So if the electric fields are pointing up and down and the magnetic fields are pointing horizontally, at any point you can find the direction that's perpendicular to both of those, and what it is outward. So the only direction that you can have the electromagnetic waves travel from this is outward in the horizontal plane here. So this is making electromagnetic waves that travel outward. Now my grandmother and grandfather used to have radio station towers, and the radio station itself was also on their property until the radio station kind of bilked them out of things. And so we had these big towers, and we were driving to Modesto. You know, our game was always the first person to see Grandma's towers because of the radio towers. You guys familiar with the radio tower? Yes? No? Okay, the radio towers are big and tall. Their height is actually determined by their frequency. You need, for optimal transmission, you need a certain relationship between the frequency and the height, which we're not going to go into. So the height's determined by the frequency. But for instance, Grandma's towers, there were 3 of them. 3 different antennae. 3 different towers. Why 3 different towers? Because you're making 3 waves, and those waves, when they meet, what will they do? They'll combine, they'll interfere in some places, like when Denford had the 2 little tuning forks that were close but not exactly the same. You had in time beats. That is, you heard it get louder, softer, louder, softer. Well, if they have the same frequency, but they're separated, you're going to have positions where they're in phase and you have constructive interference, and positions where they're out of phase and you have destructive interference. And so the reason to have multiple towers is so you can get a directionality and say, okay, we want to broadcast over here because people live there, but we don't want to waste our energy in that direction because nobody lives there. And of course, they're nice tall towers because they want the waves to go out horizontally, because there's nobody living up above them either. You don't need to broadcast your radio signal up into the sky. So that's why they're vertical towers. So there's a lot of sense going on there. Okay, next question, one we've already answered. You can answer now. What kind of wave is an electromagnetic wave? Okay, at the end, things got better. One person said longitudinal. It's not a longitudinal wave. Longitudinal waves are like sound waves, where the displacement is parallel to the velocity. I said that the electric field, which is our displacement for one, and our magnetic field, we have 2 types of displacement, are both perpendicular to the velocity. What kind of wave has the displacement perpendicular to the velocity? You can answer out loud. I'm just waiting up here. I have to check. No one? I know you guys know this. It's a transverse. When displacement is perpendicular to velocity, that makes it transverse. So what are the bottom two? What are Rayleigh waves and Love waves? We've talked about them. Apparently not enough. The Rayleigh waves and Love waves were combinations of longitudinal and transverse waves that we get in earthquake waves and seismic waves. Okay, so this is just reviewing the things we had there, that it's a transverse wave. Measuring the speed of light. PHYS experiment is one of the important experiments for actually accurately determining the speed of light. The first measurement of speed of light that at least I can recall, I think it was Galileo tried to measure the speed of light. It might have been somebody before him like that, not sure. Actually, it probably was, because I think PHYS was before Galileo. I don't know. My times are all off. The first measurement was basically a researcher and his assistant go to like mountaintops. I'm on this mountaintop, and Andrew's on that mountaintop. And I have a lantern that has a shutter on it. And Andrew has a lantern that has a shutter on it. And we have agreed I am going to open my shutter and start a timer. And as soon as Andrew sees it, he's going to open his shutter. And then when I see the light from Andrew, I'm going to stop the timer. And thus, we've measured the time for light to go from me to Andrew and back. So if we measure that distance there and back, we divide it by the time I measured, that'll give us the speed. What do you suppose the outcome was? What he determined, because I don't remember, like I said, the name of the research, but I know he was smart. What he determined was, that time is as fast as it would have been if I just relied on my reflexes. There's no difference in my reflex time and the time that I got for this. Well, my reflex time and my assistant's reflex time. And so he determined it's super, super fast, too fast for us to measure this way. At least he was honest and intelligent about his analysis. He didn't say, oh, well, remember we did the experiment, the first lab where you dropped the balls? And your timings were pretty off, right? Because of reflex issues. And he recognized, yes, our uncertainty here, got a reflex issue. I can't tell you the time. Later, I think it was Ole Romer, R-O-E-M-E-R, or maybe it's R-O umlaut, depends on who writes it. Ole Romer, he noticed that the period of Io orbiting Jupiter differed when Jupiter was closer to us than when Jupiter was farther from us. Now, it does not make sense that our distance from Jupiter would make a difference. So he chalked that up to the speed of light. And from that, you got to measure the speed of light. It was, I think it was off by about a factor of 2, but it was the first measurement. PHYS experiment is the first one that gives a really good measurement of the speed of light. And his experiment is reasonably simple. You make what we call a light chopper. That is, you have that wheel, and that wheel has evenly spaced teeth on it. And you shine light and you spin the wheel. So you have light, no light, no light. Going like that. Well, all that's doing is sending pulses of light. But then a large distance away, notice 8.6 kilometers. That's not nearby. Right? That's somewhere in the ballpark of 5 miles away. You have a mirror that reflects the light straight back. Reflects the light straight back so the light goes through the chopper again. So the light has to go through the chopper to the mirror, back from the mirror through the chopper, and then you measure the return light. Now in that case, the time for light to go from the chopper to the mirror and back to the chopper has to be equal to the time for the chopper to go through one of its symmetry rotations, or 2 of its symmetry, or 3, or so on. So it has to be an integer multiple of the rotation frequency. Well, it has to be related to the frequency. And so then he just changes the frequency and finds the frequencies where light comes back through the chopper. And he says, okay, light comes through at this frequency, at this frequency, at this frequency. That's enough data then to determine how much time it's actually taken for the light to go down and back. Now he has an accurate measurement. This isn't human reaction time anymore. He can measure the frequency of his rotating wheel accurately. He knows the distance accurately. He has the time and the distance. And so he came up with a really good measurement for the speed of light. Since then, there have been a lot of more precise measurements, things using interferometers. Interferometers is having light go down here and back, and you split the beam and have the beam come back together. And when you have constructive interference or destructive interference, you can then, determine how much in or out of phase they are. And so you change the length and measure the phase differences, and you can determine really accurately the speed of light. So from all of this experimentation, scientists have now determined that the speed of light is exactly 299792458 meters per second. I say exactly. They were measuring speed of light, they got more and more precise, and then scientists decided, wait, the meter. Remember, way back at the beginning of the semester, and I talked about standards. And we had the standard for mass is this chunk of platinum iridium that's in 2 vacuum chambers in a museum. And if you wanted to compare mass to a kilogram, you would have to take that out and do measurements. It's really impractical. It used to be that the standard for a meter, well, it started out as, I think, 100,000 per million, or something like that, of the distance from the equator to the pole along the prime meridian. That was the original. And then they made those marks on the platinum iridium rod and said, okay, so here's our meter. And then people said, wait a minute. The speed of light, we believe, is a constant in vacuum. So let's use the speed of light as our standard and then use it to calculate what a meter is. And so now the speed of light has been converted from a measured value to an exact value. That's all the digits in it. Now, just a personal statement, it makes me really sad that they didn't say, no one's going to notice if we change the 2 markings on this bar by just a little bit and make it exactly 300,000. They could have done that. Nobody would have known the difference. But no! It's much more fun to memorize 299792458 than 30000. So that's the exact value. And people still do experiments, of course, on the speed of light. But if they find a different value, they're actually adjusting the length of a meter. The length of a meter is calculated by a very large number of wavelengths of a very specific emission line from sodium. But you can do that anywhere in the world. So this is our speed of light. It's a standard, and that's in vacuum. In any other medium, the speed of light is slower. So for your homework problems, you can just use 300,000 meters per second, right? Because the difference between 300,000 and 299,790, right, to 458, it's insignificant. So if your homework, just use 3 times 10 to the 8. Don't worry about putting all those digits or memorizing them. That's something that a physics teacher does only. Okay, the spectrum of light. The electromagnetic spectrum ranges from really low frequencies to really high frequencies. You need to be familiar with these ranges. So the lowest frequency shown over on the right here, we call radio waves. Low frequency, remember, frequency and wavelength are related by this equation. Does that show up? Yeah, it actually shows up pretty good. So since frequency times wavelength is equal to the speed of light, if the frequency gets bigger, the wavelength gets smaller. So this scale shows on the top the frequencies, small on the right hand, large on the left hand. Down below, the wavelengths, small on the left hand, large on the right hand. So starting at the longest wavelengths, we have radio. So this section here, radio. Notice your AM band, your FM band, your television, those are all considered radio signals. And they have pretty long wavelengths, on the order of a centimeter out to, for long wave radio, 1,000,000 meters, 1,000 kilometers. That's kind of like your wavelength is going from here to Salt Lake City or something. Okay, that's pretty long wavelength. Hence the term long wave. For AM radio, kilometer or less. So that's like, from here to my house is the wavelength. For the long side, for the short side of AM, it's more like from me to you or, something like that. FM, it's, smaller distances. TV, even smaller. Next comes microwaves. Microwaves, like what this uses to communicate. This is emitting microwaves to a cell tower, receiving microwaves from a cell tower. That's how it communicates. Or, I have a couple students with their computers. If you're using Wi-Fi, the Wi-Fi is once again using something in the high frequencies of radio waves to communicate. So we're using electromagnetic waves to communicate a lot. You go shorter wavelengths or higher frequencies, you get into infrared. I always have to point out, I've already told you guys we came to America, the folks bought the World Book Encyclopedia, 1972, because that's when we came to America. And in it, I think it was 1972 edition, I know it's when we came. In it, it had infrared radiation and all kinds of stuff. And I, as a little pipsqueak, I read that as infrared. Because it looks like infrared. Like it's, past tense or something. No, it's infrared. Infra means below. So infrared is electromagnetic waves that are frequencies below the frequency of visible light. Our bodies are giving off infrared radiation. If we turned off all the lights, we couldn't see each other because infrared is below visible. We're giving off the radiation, but we can't see it. So let's suppose that we are soldiers and we want to see people in the dark. What do? We get some goggles that have detectors that can detect infrared radiation, and then they make a visible light picture for us to see. So then we have night vision goggles that take infrared radiation. They're essentially a little video camera. They take video and then they make a picture for us. So that way we can see things in the dark. Then we get to the visible range. Notice how small the visible spectrum is compared to the entirety of the electromagnetic spectrum. It's very small, and you have that range of colors, and you should know the range of colors. You guys probably know that, right? I should have actually written it backward because my picture is backward from this. Okay. Red, orange, yellow, green, blue, indigo, violet. In my world, it ends at blue. I don't know what the difference is between blue, indigo, and violet. Honestly, call that a weakness in me. My sister thinks it's silly in me. But we have that order of colors. Those colors are just different frequencies. Frequency for red is about 4 times 10 to the 14th hertz. Frequency for violet is about 7.5 times 10 to the 14th hertz. So we have just the different frequencies give us the different colors. We usually talk about these, instead of using frequencies, we talk about wavelengths. So wavelength. Wavelength, about 400 nanometers to about 750 nanometers. But like I said, we can talk about the frequency. Not 4, 7.5. I use 750 and 400 because those numbers make the conversion simple between frequency and wavelength. Of course, what is the real conversion between frequency and wavelength? Frequency is equal to the speed of light over the wavelength. Okay, I see my time is up. Have a great Monday. I'll see you in lab this afternoon.